Welcome back. We're going to take a look at lesson 9.3 in this video. The topic is Taylor series. Now, I remember the last lesson we were looking at creating these lovely infinite series to describe different expressions. Well, we're going to do something similar today. In this section, you're going to be finding polynomial functions that can be used to approximate transcendental functions. What are those again? Those are like sine x, cosine x, e to the x, ln x, all those functions that are not really expressed as a polynomial, right? It can't be done as a finite combination of algebraic operations, okay? So what we're going to try to do, though, however, is to approximate them, okay? So if I have a function which I call p of x, okay, and let me call that the polynomial function, and it's used to approximate some other function, which I'm going to call f of x. Okay, so like think of the f of x like sine x or e to the x. Okay, well, what they're saying is it must contain the same point with some x value, which I call c. Meaning there must be at least one place where the polynomial p of x is actually equal to the function value f of x. Okay, so think about it like this. Don't need to write this down. Just watch. If I've got this function, let me call it, I don't know, sine, right? Like that. Well, if I want to find a polynomial, I have to have one where at least there's one point on the actual graph of the function f of x. Now, I want a better approximation than that, right? So to better approximate that, maybe they should also have the same slope at that point, because then I can draw a tangent line. Remember that idea of tangent line approximation that we did earlier in the Calculus AB course? There you go, right? And that just means that the derivative of that polynomial at that value c is equal to the derivative of the function at that value c. Okay? Now, for even greater accuracy, perhaps you want the second derivatives to be equal to each other. Okay? Because then we don't have a tangent line approximation, we could have perhaps a quadratic approximation like this. Maybe that will be even a better approximation. And if you continue on and on and on and on, you might get like a cubic and a quartic and so on. Well, this whole idea is actually this idea of Taylor. And Taylor created something called the Taylor polynomial expansion. Okay? So what Taylor said is this. If that function f of x, so think about like sine x, e to the x, right, has derivatives of all orders, meaning you can take the derivatives of the first one, second one, third one, fourth one, all the way to like infinite ones, then it can be approximated by the following polynomial functions shown below. P sub n, okay, this n stands for the degree, the nth degree, or the nth order of the polynomial. And it must be centered at some value c, okay? And like what he said earlier, it has to be equal to f of c plus f prime of c times x minus c. Now, if you think about this, this is actually the tangent line approximation, okay? If I were to add to it the second derivative, it's actually this. It's f double prime of c over 2 factorial. Yes, that factorial thing comes into play now, times x minus c all squared. And by the way, if you took all this together, this is what we call the quadratic approximation. And then we can continue on by looking at the third derivative. And of course, that'd be divided by 3 factorial. And the x minus c term would be to the power 3. And so on and so forth to this general term, the nth derivative at c divided by n factorial, bracket x minus c to the power n. Okay? This is called the nth degree or nth order Taylor polynomial centered at c. And yes, it's in the box, so you should memorize this. Okay? Now, there was another person that was thinking about the same things as Taylor, but he didn't get credit for the general series. He got credit for the series when the center value is actually 0. So if I made the c value 0, that just simplifies that top function into this, where everything is now 0. And it's pretty much the same thing, but they gave it a different name. It's called the Maclaurin series, or the Maclaurin polynomial. Okay, so this is the one where if I'm taking that sine graph, Maclaurin is saying, look, my c value will always be at 0. And I'm going to start doing the tangent line, the quadratic, all that kind of stuff at 0. Okay? All right, so with that understanding, let's take a look at example number 1. I'm going to ask you to use the formula from above to create the Maclaurin polynomial. So once again, Maclaurin polynomial means the c value, it's centered at 0. To find the 5th degree one, so that means I need n equal to 5. And I want you to do this for the polynomial e to the x. All right? So we know that f of x equals e to the x. I'm going to begin by actually taking the derivatives, and not just the first derivative, which is just e to the x, but the second derivative, which is of e to the x, which is the third derivative, e to the x, and I want the fourth derivative, e to the x, and the fifth derivative, e to the x. This will be the easiest one you've done ever, okay? And now I'm going to ask you to evaluate. So f of 0, yeah, just plug in 0. So that, of course, is equal to 1, 1, 1, 1, 1. So now let's going to use that formula and build the Maclaurin polynomial. So the first term is f of 0. That's just 1. The second term is f prime of 0 times x. So that's just 1 times x. The third term is f double prime of 0. That's also 1 over 2 factorial times x. That's right, squared. And we'll continue this. 1 over 3 factorial x cubed plus 1 over 4 factorial x to the power 4. And we're going to stop at the fifth, so 1 over 5 factorial x to the power 5. Good. And that, my friends, is your Maclaurin polynomial to find the 5th degree polynomial to approximate e to the x. Okay? Now, this is a pretty good approximation for e to the x, but of course, if I were to extend it further, I get a better and better and better and better and better approximation. Now, if I were to extend this infinitely, though, as an infinite series, then actually it becomes the exact correct value instead of the actual approximation. So remember, a transcendental function is one that I cannot make a polynomial that is finite, but look, I'm saying now it actually can be infinite. So here we go. What would the infinite one be? It'd be 1 plus x plus, just writing the same thing from above, right? 2 factorial plus x cubed over 3 factorial, I'm going to go plus dot 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 dot, plus the general term, which is x to the n over n factorial, right? That's the general way of describing every single one of these terms when I add together, and then plus dot dot dot. As long as you have this dot dot dot, this is actually equal to the function e to the x. Okay, exactly equal. All right. So the general form of the Taylor and Maclaurin polynomials can be extended. Yes, we can extend it to actually create what I call the Taylor and Maclaurin series. So all you need to do is take that polynomial from before and just extend it. Let's keep going. So the only difference here is really this part at the end, plus dot dot dot. Okay? That plus dot 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 means this goes on infinitely forever, and if it does go on forever, then it actually equals the original function. And the same idea with the Maclaurin series. Of course, we have a caveat that the derivative has to exist for all the different values, okay, or all the different orders. Okay, so these formulas now allow us to form power series. Why do we call these power series? Because they're powers of x. Okay? For functions that cannot be written as geometric power series. So last day we just looked at geometric power series. Very limiting. Okay, but now I've opened up the whole world for you. You can now find power series for pretty much any function that's out there, as long as you can take its derivative. So here's example number 2. Here's cosine x. Okay, I'm going to ask you to use the formula for a Taylor polynomial to find the 4th order polynomial, and then also the Taylor series. Pretty much the same idea, right? What's the difference again? Series plus dot dot dot. Okay, for the function f of x equals cosine x, centered this time at c equals to pi. You ready? All right. Let's do this. F of x equals cosine of x. What's the derivative? Negative sine x. Good. What's the second derivative? What should be the derivative of negative sine x? Negative cosine x. What's the third derivative? The derivative of negative cosine is positive sine. And the fourth one, back to regular cosine of x. And now evaluating all of these terms or expressions at pi, cosine of pi is just negative 1. Sine of pi, well, that's 0, so negative 0 is still 0. Cosine of pi, that's just negative 1, so negative 1 is positive 1. Once again, 0, and also negative 1. So now, as we build the polynomial, the fourth degree one, let's begin. The first term is f of pi, which is negative 1. And then the next term has a coefficient of 0, so 0 times x minus c, which is just pi. And then the next one would be 1 over 2 factorial. And then that would be x minus pi all squared. The third one would be the third derivative, 0 over 3 factorial, x minus pi to the power of 3. And then the next one would be what? Plus negative 1 over 4 factorial, x minus pi to the power of 4. And you may be thinking, well, why did you put those zeros there? Right, I didn't actually need those zeros there, so you could have just simplified this to negative 1 plus 1 over 2 factorial, x minus pi all squared, and then minus 1 over 4 factorial, x minus pi to the power of 4. Okay. Now, for the Taylor polynomial, you stop here. Done. Okay. Yet for the Taylor series, well, you'd have the same thing, but what's different? Yep. Plus dot dot dot. Okay. Going on forever makes this series equivalent to the function f of x. Okay. Now, why is this handy? Well, did you actually know that your calculator actually calculates sine and cosine like this way? Yeah, it doesn't have all those values built into the calculator. It can't go cosine 0, cosine 0.01, cosine 0.02, and all that. It's actually built in this polynomial. Of course, that allows it to be accurate to whatever 12 decimal places or whatever it is in your calculator. But it's built in this way to calculate these transcendental functions. So in example number 3, can I actually use the Taylor polynomial that we just created? And can you actually approximate cosine of 3? So take the polynomial from above, negative 1 plus 1 over 2 factorial, and now I'm going to replace x with 3, so 3 minus pi all squared, minus 1 over 4 factorial, 3 minus pi to the power of 4. Okay? And then if you were to evaluate this, I guess you don't want to do it, do you? Okay, fine, I'll do it for you. It would be negative 0.989857. Okay? But interestingly enough, if I were to bring up my graphing calculator and actually ask you to type in cosine of 3, look at the answers. That's pretty good. Negative 0.989999, and that's my approximation. I'm pretty happy with that. Okay? And that's only with the first 3 terms. Imagine if I had more terms. I'd get an even more accurate answer. Okay? Alright, so I'll say this is pretty close to the real cosine. Right? So I'll say note cosine 3 is actually negative 0.98999. Pretty close. Yeah. Okay. I think you can try example number 4. Yeah? Go ahead. I would like you to work on this. And then once you're done, come back and double check your answer with me. Because I think you are now capable of doing this and doing this well. Okay? So this time it says use the formula for a Maclaurin series. Why is this Maclaurin this time? Yes, I hope you see the C value is 0. Makes it a little bit nicer. Okay? So go ahead and try this, and then, like I said, pause the video, do it, and then come back and check. Just writing all the derivatives right now. Just evaluating all these derivatives right now. Now plugging it in, so f of 0 is 0 plus f prime of 0 is 1 times x plus the second derivative, which is 0 over 2 factorial times x squared, plus the third derivative, which is negative 1 over 3 factorial x cubed, plus the fourth derivative, 0 over 4 factorial x to the power of 4. Whoa, what happened there? And then also we'll do one more plus 1 over 5 factorial x to the 5. And then if I ask you for the series, definitely we need a plus dot dot dot. So let me just simplify this. I think you get x minus x cubed over 3 factorial plus x to the power of 5 over 5 factorial minus x to the power of 7 over 7 factorial. I can keep going, can't I? I won't, but you could also come up with a nice general term if you really wanted to. Okay, if you think about this, what can I do as a general term? I know I didn't ask you for this, but I'm just going to do it anyways. Can you see how every second term is negative? So it alternates from positive to negative, which means I probably have to have this term negative 1 to the power of something. Okay. If I considered this the first term, and this the second term, and the third term, and the fourth term, you'll see that every even term is the one that is negative. So I think I'll make my exponent like this, not just n, but n minus 1. Okay? You'll also hopefully notice that the x exponent seems to be what? Hey, wait a minute. Maybe I'll make that, yeah, I'll do it like this. 2n minus 1. Can you see that? Right? For instance, here's my third term, right? 2 times 3 is 6, minus 1 is 5, right? And then here's my third term, 3 minus 1, that's 2, so that's positive, good. And then I need a denominator, so don't forget the denominator is something factorial. It's that same 5, so that's 2n minus 1 factorial. So this is the general term, and I can go plus dot dot dot, and that would be totally fine. Okay, that would be a very good, exact answer for sine x. Cool? Cool. Now, by the way, this is not the only way you can write this. Okay, I just chose that because I denoted the first term as x, the second term as x cubed over 3 factorial, and so on. Okay, just to let you know, I have also seen this over here. So I have seen something like this, where I will write down these terms again, but I'll consider this like the 0th term. This is the first term, the second term, and so on. Because if you do that, then what you'll see is that instead of having negative 1 to the power n minus 1, I can say now, oh, it's the first term, the what? Third term, the fifth term, right? So I can just create it as n, because when n is odd, I have the negative. When it's even, I have a positive term. Okay? And then in this case, I can also write down x as not 2n minus 1, but 2n plus 1, because that's another way of describing an odd exponent, right? So think about this term here. 1, right? 2 times 1 is 2, plus 1 is 3. Okay, and then yes, we have to divide by that exponent, or not the exponent, yeah, the exponent as a factorial, so that's just 2n plus 1 as a factorial. Okay, so I've seen it like this before as well. So once again, to describe the general term, sometimes there are many ways you can do it, so don't freak out if your answer is not exactly the same as what's perhaps written in the answer key. Okay, all right, one last one before you do your assignment. Bravo, you've made it to the end. Example number 5 here says, find the power series for f of x, this time centered at c equals to 1. And this time I'm telling you that, oh, look, f of 1 equals to 2. So I gave you that first value. And then now I'm saying f of the nth derivative. So every nth derivative is given by the formula n factorial. Okay, so you don't need that first column here anymore. You don't need that because I gave you the expression. So all you're doing now is actually creating the next column. So think about it as like f prime of 1, f double prime of 1, f triple prime of 1, and hopefully you'll see some pattern. I certainly do. That's 1 factorial, which is just 1. This is 2 factorial, which is just 2. And this is 3 factorial, which is just 3 times 2 times 1, right? Or 3 factorial, which is 6. So, trying to find the power series now. F of x is equal to, well, it's centered at 1, so f of 1, I guess I should write this out right, f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 over, don't forget 2 factorial, x minus 1 squared. I'll write out one more term, f triple prime of 1 plus 3 factorial x minus 1 cubed, and don't forget plus dot dot dot, because it's a power series. Then if I were to evaluate this, f of 1, yes, that's equal to 2. F prime of 1, that's 1 now, so 1 times x minus 1. F double prime of 1, that's 2, so that's 2 over 2 factorial. Okay, good. We can simplify it in a sec. F triple prime, that's 3 factorial, or 6. Oh, so that's really just 3 factorial over 3 factorial. Oh, that's nice. I hope you can see that this is just 2 plus x minus 1 plus x minus 1 squared plus x minus 1 cubed, and so on and so forth. And if you want to write that even nicer with a summation symbol, don't have to, but if you wanted to, space, 2 plus, and I'll say the summation, and the expression is just x minus 1, right? So the power n, where n equals to 1, and because this is an infinite power series, we're going to infinity. All right, that's your introduction to Taylor and Maclaurin series. We're going to look at this again in the next lesson, so make sure you do your homework and do it well. Until then, bye.